Good afternoon, everyone. About this title, when I decided to give this title, I was thinking about how I decided to, or when I started to be interested in stars, and it came back to when I was a kid. So anyway, I had just, more seriously, this talk is about age rotation and magnetic activity relationship. And I'm mostly going to focus on what seismology can bring to the picture of this relationship. So stellar ages, why are they so important? I think the past few days, many people have already talked about that a little bit, but I just wanted to remind you about the fact that these ages can be important to study planetary system evolution or star formation history, for instance. But unfortunately, these stellar ages are very difficult to determine, especially for low-mass field stars. So for a star that belongs to a cluster, because these stars are coeval, it's easier to determine their ages more precisely compared to field stars. Besides, you also some stellar phases can happen more or less rapidly in the evolution of the stars, so depending on the stellar mass, which makes some phases of the star easier to be dated compared to other phases. So here is just a brief outline of this talk. So I'm going to start with a little bit of history on the age rotation activity relations. Then I'm going to show you some different methods that we can use to measure rotation and magnetic activity. And then I'll show you what kind of inputs we can get from seismic observations. And I'll finish with some highlights on the recent results with the Kepler mission. So let's start with some history. So I'm not going to talk about the whole history of relation between ages, magnetic activity, and rotation. So I apologize if I forget anything, but this is my biased point of view, maybe. How do we measure ages? In the past, the easiest way was to study clusters because stars are coeval. They have a homogeneous chemical composition, so they are it's much easier to determine more precisely ages for these stars. Then you also have people who started to study the lithium abundance because we know that lithium is destroyed very easily in stellar interiors. So this has been used as an indicator of the age of the stars, especially for low mass field stars. And so when you have a star that has a very low lithium abundance, it means a very high lithium abundance, it means that it's a very young star. But on the other hand, for massive stars, you don't expect to have lithium depletion, but there are a few stars where we have measured a high lithium abundance. So there is a kind of bimodality that appears for this lithium abundance, and this is still something that is puzzling me. So I think that we cannot really rely on the lithium abundance to really get very precise ages. But at least high measurement of lithium can give us information about a low limit on the ages of the stars. So this is mostly for clusters, but then for field stars, we can still use isochrones to determine the ages of the stars. I'm going to talk about the seismic analysis to get ages. And then some people have started to use other parameters to get ages of the stars, like the rotation, the magnetic activity. I was trying to find a word similar to gyrochronology, so Chromospheric chronology, chromochronology. Anyway, so that's the idea of using magnetic activity and rotation periods to determine the ages of the star. So let's come back to what 40 years ago managed started to do by studying a few young clusters for which the ages were known. So here you have, for these clusters, there were measurements of lithium as a function of the age, the rotation period as a function of the age, and the magnetic activity. And in particular, he derived a law with the age showing that the rotation period is inversely proportional to the square root of the age of the star. And then a few theoretical works were done further. But there is still some dependency with the stellar mass. Here you have this plot from Kraft in 1967. This is an HR diagram, and you can see that stars that were more massive than approximately 1.25 solar mass have a much higher rotation period compared to lower mass stars. So this is the Kraft break, and this can be easily understood by the fact that because these more massive stars have a thinner convective zone, they are less affected by the magnetic braking, and so they are less slowed down compared to the lower mass stars. The last 10 years, more works have been done on these relationships. In particular, Barnes and collaborators studied a few more young clusters. And here you have the rotation periods of the stars of these clusters as a function of the color, B minus V. And here you have the cluster that are put in the increasing age. And in these last two panels, you have field stars, young field stars and old field stars, for which there were measurements of rotation. And so Barnes and collaborators showed that there were two distinguished sequences that came out from these plots. You have this convective sequence corresponding to the fast rotators, and these correspond to convective, fully convective stars, and you can see that they are mostly present in the very young clusters. And on the other hand, you also have the interface sequence, the interface dynamo, which are slower rotators, and for which you have mostly large-scale dynamos, and they correspond to coupling between the radiative zone, the convective zone, and the exterior of the stars. And so from these observations, they derived a new relationship between the rotation period of the stars and the age, and there is also a dependency with the color of the star. Then there were more works that were done where people were looking for a relationship between the magnetic activity of the stars and the age. So this is, for instance, what has been done by Mathur and Hillenbrand in 2008. So here you have the age as a function of the magnetic index R prime HK, which corresponds to measurement of the chromospheric activity of the stars. And this was done for a few young clusters and a few field stars, for which the ages were obtained with isochrones. And you can see that different relationships were derived between these two parameters, and Mathur and Hillenbrand added a dependence with the color as well, similar to what Barnes and collaborators did. This is the more recent work done by Pace last year, who also studied the chromospheric activity of a very large number of stars, cluster stars, and a few hundreds of field dwarfs, where ages were obtained with the Geneva-Copenhagen survey, and for which there were also observations of the chromospheric activity indexes. And one of the results of this paper was that apparently that seems that there is no evolution of the magnetic index after 1.5 gigayear. So well, this can still be biased by the fact that we are observing the stars only at one given moment of the cycle, so there can be we can be observing it at minimum or maximum activity, so that can also bias the results. So let's move on to how we can measure rotation and magnetic activity of the stars. So concerning, we can use classical observations like spectroscopy, spectropolarimetry, based on broadening of the lines to get B sin I, which is dependent on the inclination angle of the rotation axis of the rotation axis of the star. Also changes in the emission in the absorption lines like LCMHK, H alpha, which has been shown, for instance, by Katia earlier. And from spectropolarimetric observation, you can measure the magnetic field of the stars and its topology. And that has been done for quite a number of stars lately. And concerning the light curves, so we know that stars that have spots crossing the visible disk create a modulation in the light curve. So that's the sun with during the maximum of activity, and you can see this modulation that corresponds to the rotation period of the sun. On the other hand, if there is no activity, if you're observing the sun during the minimum of activity, then you have a flat behavior in the light curve, and you can't measure the surface rotation. So these two parameters are tightly related, linked to be able to measure the surface rotation. So from these light curves, you can compute periodograms to get the highest peaks in the periodogram to measure the rotation period. You can also do some time frequency analysis or autocorrelation function. And one thing that I want to point out here is that with with the periodogram, one of the issue can be that you're measuring a harmonic of the mean rotation period. So, and this is something that we can, that the time frequency analysis and the autocorrelation function can get rid of. So concerning the magnetic activity, how can we measure it using light curves? So here you have an example of a light curve, the flux as a function of time of a Kepler target. Because these spots are creating a modulation in the light curve, you can have one way of getting an index of the magnetic activity by taking the standard deviation of the time series that I call here SPH. But because I showed that there is a very tight link between the rotation period and the magnetic activity of the star, we can also use the knowledge of the rotation period of the surface of the star to get a more precise index of the magnetic activity. And this is what we have done by taking some subseries of the light curve of length an integer times the rotation period to be sure that we are really taking the magnetic activity of the star, and computing the standard deviation of all these subseries and taking the mean value. With this method, we can also compute a contrast number, which is basically which takes into account the fact that we have the highest standard deviation and the lowest standard deviation in these subseries. So it's just a ratio between these two values. Here, this is the time frequency analysis of this light curve using wavelets. So you have the period and the time and the wavelet power in color code. So basically it represents the correlation between a given wavelet with a given period and the time series. So the highest correlation is represented in red, for instance, and the lowest correlation is represented in blue. So here for this star, for instance, you can measure a rotation period of 2.5 days. If you project this wavelet power spectrum on the time axis, you get something similar to a proxy of the magnetic activity of the star. And you can easily see that you have a minimum of activity, an increase of the activity, and again a decrease of the activity. So this is an interesting way of studying the magnetic activity of stars. Besides, if you look at this wavelet power spectrum, you can also see that there is a change in the rotation period. So you can also have some kind of butterfly diagram by using this technique. So let's come to what seismology can bring into the picture on this relationship between age, radiation, and activity. We have seen in the past few days how we can use stellar models that include different physical processes. This is a non-exhaustive list of physics that can be included in these models. And we try to fit these models to the observables that are available. So these can be spectroscopic observations, effective temperature, metallicity, but also seismic observables, delta nu, nu max, and the individual frequencies of the modes. So you can use different methods. You can use grid modeling or also other techniques like the genetic algorithm that's used in the astroseismic modeling portal. And these have been used on a very large sample of stars, showing that we do improve the precision on the mass, the radius of these stars, but also on the ages of these stars. Then we have also seen in the past few days that rotation has an effect on the modes. So here it's just to show you how the rotation lifts the degeneracy for the modes. So for an example, here you have an L equal 1, and because of the rotation of the star, you have splitted modes. So here you have M equal 1 and M equal minus 1. And the difference of frequency is called the rotational splitting, which is proportional to the internal rotation of the star. Of course, this also depends on the inclination angle of the stars. So you also have to take that into account. And here I just wanted to show you that using a lot of modes with a lot of rotational splittings, you can do inversions to get a rotation profile, and that's the case for the Sun. Then magnetic activity also affects the modes. So here I just wanted to show you how for the Sun we know that the amplitudes and the frequencies of the modes are affected by the magnetic activity. So here you have the amplitudes of the modes as function of time, the frequencies of the modes as function of time, and the red line corresponds to the sunspots number, so a classical magnetic index. And we see that there is this nice correlation between the frequencies and this sunspots number, and an anticorrelation with the amplitudes of the modes. So knowing that, we did some analysis of one of the CoRoT target HD 49933, which has a rotation period of 3.4 days. And we measured, similar to the Sun, the amplitudes and the frequencies of the modes as function of time. So this star was observed in 3 runs. Here I'm just showing the first 2 runs. And you can see that we have also this very nice anticorrelation between the amplitudes of the modes and the frequencies, suggesting that we indeed have a magnetic cycle going on this star. Unfortunately, we didn't have enough data to get a very precise measurement of the cycle period for this star, but we had in parallel some spectroscopic observations confirming that the S index is compatible with an active star. So that's what seismology can do for rotation, activity, and ages of the stars. And so here I'm just going to present some highlights of the Kepler results on this relationship between these 3 quantities. So here, this is one of the first paper I think that came on the clusters observed by Kepler concerning rotation and age relationship. So this is NGC 6811, which has an age of approximately 1 gigayear. And so Mabel and collaborators measured the rotation period of approximately 71 stars, which is represented here as a function of B minus V. And in orange, you have overplotted the empirical color period relationship that was extrapolated to 1 gigayear using the Skomanic law. And you can see that this relationship doesn't really agree with what is observed for this cluster. They also represented the results of theoretical rotational evolution models computed by Barnes. So these 3 colors correspond to 3 different initial rotation period in the ZAMs. They seem to agree better with the observations, but we still have to understand, to study these relationships. I'm going to go very fast with this one because there is a talk that's going to present that. So I just wanted to show you that surface rotation periods have been measured for a very large number of stars using the autocorrelation function. And here you have the period as a function of the effective temperature with some theoretical relationships for different ages. According to this plot, we could say that there are few stars older than 4.5 gigayear, and most of the stars seem to be younger than 1 gigayear, but there could be one of the issues is that most of the masses and the evolutionary stages are put in the same plot, but we need to remember that these different evolutionary stages and masses behave differently. So that could explain this plot. Then this is a result on solar-like stars for which we had astroseismic observations, constraints on the mass, radius, and ages. So this is a sample of 540 solar-like stars for which we measured the rotation periods using wave analysis and autocorrelation function. So here you have an HR diagram showing this the sample of stars for which we could measure this rotation period. So it's approximately 300 stars, and the different colors correspond to hot stars in red, cold stars in blue, and subgiants in green. So here I just wanted to show you a histogram of the rotation periods and the SPH, the magnetic index of the photometric data. And one thing that I want to point out is that indeed for the hot stars, we do have the fastest rotators, which agree with the Kraft break. Concerning the magnetic activity, we also see that most of the active stars are also these hot stars. And I invite you to go and see the poster by Tigran Selliet's poster 110. So from these measurements, you can also start to study rotation period and ages. And so we took a subsample of stars for which we had more precise ages using the astroseismic modeling portal, so it's 15 stars. And we just computed the fit of these observations and compared them to relationships that exist between rotation period and ages, and they seem to agree quite well. And I have to remind that these stars are only cool stars. Then there were also some magnetic activity observations for 22 solar-like stars. This has been done by Karoff and collaborators with the Nordic Optical Telescope. And here there was also trying to get relationship between the magnetic activity against the age of the stars. So in green, you have the ages that were determined by the astroseismic modeling portal, while in black, it's they correspond to ages obtained with a grid model. So the biggest differences come for the younger stars, for which apparently the grid model doesn't capture the young age. And finally, from this sample of astroseismic stars, there were a few stars that could be considered solar analog candidates. So there were 8 solar analog candidates for which we had rotation periods. And with Don Nascimento and collaborators, we tried to see if we could get a larger sample of solar analogs candidates based on the updated Kepler input catalog. And so that led to to 22 stars for which we could measure rotation periods. And here you have the inverse of the rotation period as a function of the age. So we have, in the filled circles correspond to stars where we had seismic ages, while the open circle correspond to isochrone ages. So they seem to agree quite well with known relationships between age and rotation period. And this is a paper that just appeared on arXiv. So to conclude, what I want to focus on is that so there were different relationships that were derived between age, rotation, and magnetic activity using classical observations, but now we have the opportunity to study field stars because it was done mostly for young clusters, and with seismology we can get very precise ages. We can also study rotation periods, magnetic activity, and one thing that we need to keep in mind is that we need to take into account the evolutionary stage of the stars, the masses, because all these different categories of stars might have different gyrochronology relationships, magnetic activity relationship as well. So I thank you for your attention.
Thank you very much. Any questions for Savita? I see one in the green shirt there.
Thank you for the nice talk. I have a question concerning the age, activity, and period relations. So age is not an observable, we know, and is model dependent, in fact. So testing different physics in the models, how would impact the determination of the age in this case, and so the scaling relations themselves, and how reliable and can we consider these relations between these parameters?
Yeah, actually that's something I forgot to say, that when you are using the stellar models, of course it's for a given physics, and the ages are of course dependent on which physics you are putting in the models. So I can't tell you exactly how it's going to change this relationship. We haven't tested I haven't seen how different input physics is going to change the ages, but it will definitely have an impact on the relationships. Yeah.
One more question there?
Yeah, I'd like to give a little bit of an exoplanetary point of view. For a lot of objects that we're studying a lot are hot Jupiters, and they're very close to their stars. And generally, gyrochronology is used as one constraint among others, but sometimes an important one to give a limit on the age, on the possible ages, and then derive more precise stellar parameters. But we have to be careful that some stars can be spun up by their planet, and then it can mess a lot of things, calcium also indicators, the rotation rate. I wonder if there are any objects that could be observed with seismology, with close-in planets, and so for which we could test directly whether they have been spun up.
I think it's possible. I'm not aware if there is any work that has been done on that side, but I'm sure it's possible to study these stars, and actually that would be interesting to see how these relationships can be different, because you have planets around these close planets around these stars, and that could maybe help if we manage to do that for a sample where we know there are planets. It can help to see some outliers in our plot, and say that they might have planets actually. So that can go on both ways.
I know there are ongoing efforts to do the detailed astroseismic analysis and get age estimates, and also people looking for surface rotation periods for KOIs, but I'm not sure that any of those that have been done so far have close-in massive planets, but I guess there'll be a talk by Victor Silva-Aguirre on that tomorrow. I think we're going to have to move on to the next speaker, so let's thank Savita again.